And this is just kind of reviewing of what we're saying before we get into our formal definitions. Right? The NP-complete problem is a large class of problems. Industry would love to solve them. We don't know how to solve them in polytime. If you could solve one in polytime, you could solve them all in polytime. If you could prove you couldn't solve one of them in polytime, then it would give you that you can't solve any of them in polytime, which is probably the case. Why is this useful? If your boss comes to you with a problem, you can say, very likely there's not a fast algorithm for it that finds the best schedule, and or else I would have a fast algorithm for all NP problems, in which case I wouldn't be working for you. Right? Another important thing is cryptography. So one NP-complete problem, one part problem is I put in my password and they store something in the table on the computer that's not my password, right? And when I type in my password, it runs some program, and then they check to see the output corresponds to what's output in the table, right? Now, an NP hard problem is given what's in the table, does there exist a password which will lead to that in the table, and can you find it, right? So if you had an algorithm for SAT, then you could break all cryptography, right? And so in some ways, should you be wishing that you had an algorithm for SAT? Well, in some ways it would solve a lot of computational problems, and that would be amazing. But we would lose privacy. We would lose online banking. It would really be sort of a problem.
We showed that between SAT and graph coloring, there is a linear transition that can be operated. Those for cryptography and SAT, there is a linear algorithm that allows us to pass from one to another.
Well, that's what we did. We gave you given a circuit, we gave you a graph that was linear in size to the circuit.
It's easy because the circuit is kind of close to the graph.
Yeah.
The more the problems are different, then maybe the more difficult to have a linear.
Yeah. Yeah, all these, in fact, what we're going to see later is the NP-complete guys, the ones that are, if you can do them, you can do them all, and they're all equivalent. Pretty much you come up with any new problem in NP, it's either complete or it's polynomial. There's very few problems that are in between. They're all very quick reductions from one to the other. There's huge books on reductions from between these complete problems. All right, so remember these are the classes that we want. And let's review the right, polynomial. What does it mean for a problem to be polynomial? Well, there exists here, I'm using A for algorithm instead of M for machine, but there exists an algorithm such that all inputs, it gives you the right answer. And moreover, there's a constant C, maybe 2 or 3 or 4, such that the running time of the algorithm on any input is bounded by the size of the input raised to the power of C. Right? So we usually use N to denote the size of the input, right? So this is saying the running time is N squared or N cubed. Could be N to the 100. It's still polytime. Right? So this class NP, given an instance, as I say, there's an exponential number of possible solutions. And each solution is either valid or not valid, or has some cost associated, and you want to get the one with the best cost. But we're going to assume it's either valid or not valid. And the output is going to be, yes, there's a valid solution, or no, there's not a valid solution. Right? And in the yes or no version, you don't have to return the solution. Right? And now, how do you know if if a solution is valid or not? Well, we have a quick program called valid, where if you give it an instance and a solution, it very quickly tells you whether the solution is valid for this input. Right? Given a circuit and an assignment, we say, does the assignment satisfy the circuit? Given a graph and a coloring, is the coloring a legal coloring? Right? So for example, for network flows, we had, given a graph and an integer k, we want to know, does the graph have a flow of size k or not? Right? And that problem, right? That problem happens to be in poly time, right? But other examples, SAT, right? Given a circuit, does it have a satisfying assignment? Right? The instance is a circuit. The solution is a satisfying assignment. A yes instance is a yes instance if it has such a satisfying assignment. Right? And there's this program, valid, which will tell you it's a satisfying assignment. What? Am I going too fast? Okay. I'm going to slow down now, everybody. Take it easy. All right. So, what do we want to say now? We want to say the problem SAT, given an input, right? It's a yes instance, if and only if there exists a solution, there exists a witness, a proof, there exists an assignment such that it's a valid assignment. Right? Does that make sense? So, one of the things that I want you to learn is the definition of a problem being an NP. All right? So here, put a star on this page. Right? A problem is an NP. Right? A problem is in this blue circle. If it can be expressed as follows. If there's some polytime algorithm called valid that takes as inputs an instance and a solution and tells you whether the solution is valid for the input, and then the problem in question, what are its yes instances, right? Its yes instances, an instance is a yes instance if and only if there exists a valid solution. Right? Is everybody getting this definition? All right, so for example, graph coloring is in NP because a graph is a yes instance if there exists a coloring which is valid for the graph. Right? And you can quickly test that a coloring is valid for the graph. A SAT is an NP problem because a circuit is a yes instance if there exists a solution, an assignment that satisfies it. Right? Scheduling is an NP problem because a bunch of courses is a yes instance if there exists a schedule that's a valid schedule without conflicts. Right? People getting the feeling of this? Did people get the definition? All right, so now let's formally define what a non-deterministic Turing machine is without getting too worked up about it. Right? A deterministic one moves deterministically. Given, you might know Descartes, he said the universe is a clock. If you knew exactly where every particle was and how fast it was moving. What? Wasn't Descartes? Laplace. All right. Anyway, Pretty sure it was Descartes, but who cares? I've been saying Descartes for years. I can say somebody else. All right, so the question is the future determined? And people got upset because then we don't have free will, right? That whole question. But here, if you know what the contents of the tape is and where the head is and the state of the Turing machine, if it's a deterministic Turing machine, then the future is completely determined, right? Well, in a non-deterministic Turing machine, there's given the state and the character you're looking at, there's a set of things that the Turing machine might do next. All right? And we say that the non-deterministic machine accepts its input if what? If there exists an accepting computation. Right? So, so the way I think about it is you have given an input, then what the non-determinism does is to guess what the solution is, right? And then checks to see whether the solution's valid with the valid program, right? And if there exists an accepting computation, that means there exists a solution which is valid. Right? Which means that the instance is a yes instance. And of course, if you had a fairy godmother, she would tell you which way to go. Right? Everybody buy that? So, this is just saying it again. If the input is a yes instance, the fairy godmother, right, can give you a small witness solution proof that it's a yes instance. Right? So I like the story of my boss gives me an input, I go home to my fairy godmother, she gives me this proof, I go back to my boss, and my boss is convinced that it's a yes instance, right? But if it's a no instance, then there's likely no such proof, right? There's nothing that the fairy godmother can give to me for which I can prove to the boss in poly time that there's no solution, right? The only way to know that a circuit is not satisfiable is to try all inputs. People following this? All right, so Cohen P over here is the flip of that. If the input has is a no instance, then the fairy godmother has a proof that it's a no instance, right? But if there's a yes instance, then there's likely not a proof. Right? So sat lives over here and not sat lives over there. Not sat, of course, meaning given a circuit, it's a yes instance if it doesn't have a satisfying assignment. All right? Oh, I just added these slides yesterday. Based on the morning class. All right? So let's look at 3 problems, and your job is to tell me whether it's in NP or in co-NP. And let me just tell you a warning. Most people in the morning got it wrong. All right? So here, what SAT is, it's the set of circuits, right? The yes instances to this problem are circuits for which there exists a satisfying assignment such that the circuit on this assignment is a true, right? That's SAT, right? And why is that problem over here? Right? If it's a yes instance, the fairy godmother can give me a proof, right? Excellent. So that guy, if it's a yes instance, the fairy godmother, there exists a solution for which the fairy godmother can give me a proof. And so SAT lives up there. All right, here's another problem. Not SAT. Again, the inputs are circuits, and it's a yes instance if every assignment is outputs false. Meaning, it's a no instance if there's an assignment that outputs true. Right? So is this, where does this problem live? Co-NP. Why? Because the no instances have a witness. All right? Now, you should all get this. Everybody think about this one. Okay, here is some new problem. And it's a circuit such, it's a yes instance if there exists an assignment such that the circuit outputs false. All right, so think about this problem. Is this problem in NP or in co-NP? How many people think NP? How many people think co-NP? How many people have no idea? All right, come on, guys. What? If it's a yes instance, what would the fairy godmother give? Well, let's just say, what's the fairy godmother going to give you as proof? Right? There exists something. She's going to give you the S that exists. And what's that S that exists? It's an S that for which the circuit gives you false. And is that going to witness this being a yes instance or a no instance? It's a yes instance. I don't care that this word false is up here. Don't get confused by this being true and this being false. The fact is, if this is a yes instance, right? If there exists a solution, then there exists a witness. And the witness, right, S is a witness, but it's a witness of Si being a yes instance or a no instance. It's witnessing it being a yes instance. Right? Are you with me here? No. This is the set of instances. The yes instances are the instances for which there exists something that you can test. And I don't care what the test is. The fact is, there exists something. The fairy godmother can give it to you, and you can test it. Right? So, on the yes instances, in fact, let me make a general, bold statement here. It's an NP if they're talking about existing something. Right? The yes instances, there exists something. And the no, and it's in co-NP if for all. All right? Now, I meant to put on another thing in the slide, then I forgot. Now, if it said it's a yes instance if there exists an X for all Y, right? Then where does it live? Right? If P is the set of C's such that there exists an X for all Y, valid C, X, Y. Right? She could give you the, if it's a yes instance, she could give you the X. Right? But how do you check for all Y? Right? If it's a no instance, right, then how do you check all X's? So this lives in the void up here. Now, of course, this void is exponential time, right? It's exponential time because you can try all x, y's in exponential time. All right? Yeah?
Those your technique, those work for recognizable and co-recognizable?
Yes. Yes, in fact, we're going to get there in a slide or two. Wait for a slide or two. Yeah?
So what if we took the not-sat problem and we said for all assignment S, there exists... Wait, no, that would be...
For all assignments S, the output is true.
What if we added an exists quantifier after that? But like not that problem because it wouldn't make sense. But what if we had a statement that said for all, there exists...
Yeah.
Would that also...
If it's for all exists, then it would still be a problem.
Okay.
All right, so we're just doing this again. Network flows. There's a witness of the yes. Given you don't know what network flows is, but it's a bunch of pipes, And you want to know, can I push this much water through the pipes at a certain rate? Can I push them through at a rate of K gallons per minute? And if I tell you that how to flow the water, then that's a witness of yes. And if I tell you a cut through the pipes where you can't flow that much, then that's a witness of the no, right? And so in this case, remember we had before that if you're here and you're here, then you're here, which there's certainly intuition to that. And my father believes that's the case. But if that were the case, then our cryptography system that we currently use with prime numbers would fall apart. So most people don't believe him. All right? So in general, just because you're an NP and co-NP doesn't mean, it means you're likely NP, but it doesn't always mean you're NP. All right, so polytime, right? Why is polytime a subset of NP? Well, NP, you can do it in polytime if you have a fairy godmother. Well, if you can do it in polytime without a fairy godmother, that's even better. Right? Now, why is it a subset of exponential time? Well, because the solution has to be polynomial in size of the input. Right? So if your instance has size n, then the solution has to have size at most, say, n to the 1,000. And so then, in time 2 to the n to the 1,000, you can check all witnesses. Yeah?
N to the 1,000 is the official definition of just an arbitrary number.
That's an arbitrary number. Polytime. Polynomial. Right? So that's why you can do it in exponential time. Usually, in most reductions, the size of the solution is linear in the size of the input. But, right? So, computable, right? We know the halting problem. Now let's talk about recognizable. You were saying, how does this recognizable class compare to this class? Well, here, in both cases, an instance is a yes instance if there exists a solution that proves that it's a yes instance. Right? Here, given a Turing machine and an input, the solution is a halting computation. Right? The proof that a Turing machine halts is a halting computation. Right? And here, a proof that a circuit is satisfiable is a witness. In both cases, the computation is a witness and the assignment is a witness. Right? What's the difference between this class and this class?
One is computatable and the other is not.
Well, how big can the witness be here? Has to be about the size of the input. How big can the witness be here? Yeah, big. Right? It has to be finite, but it can be arbitrarily big. Right? Given it a little Turing machine and a little input, the running time could be unboundedly big, but still finite. Right? So here the witness has to be finite. Here the witness has to be about the same size as the instance.
So any river.
Um,
The input should be any river.
NP you can decide if it's not recognizable, you can't decide if it's not recognizable.
Oh, if you gave me here, valid runs in the size of the input and the size of the solution. It's probably fast, right? But here, here it has to be polynomial time in the size of the input. Does that answer your question? No. What were you saying?
You can prove that there doesn't exist an assignment which is the circuit is true by trying 2 to the n combinations, but you can't prove that it's not halting.
Yeah, no, you're wrong there. Why is the halting problem recognizable? Is that you try all computations until you find a computation that halts it. Right? you can enumerate all the computations, and if it's a yes instance, there's a computation and you'll find it. The difference is here, maybe this is what you're meaning, is here there's only exponential number of solutions, so you can try them all in a finite amount of time and you can say no. But here, if it's a no instance, you can't say no. Yeah, here if it's a no instance, you can say no. But you can say no only in exponential time. And that's basically, the size of the universe. So for all practical purposes, if I think of myself as a poly guy, then I can check yeses. I can't, All right, so here, this is what I said. An input is a yes instance. If M halts an I, the computation is a witness, right? An arbitrarily long but finite. No instances don't have witnesses. And co-recognizable is the flip. All right, so now we're going to talk about what it means for a problem to be NP complete. Any questions so far? All right, remember we talked about recursive complete, not recursive, recognizable complete. So this is the same idea. To be NP complete, it can't be too hard of a problem. It has to be an NP. And to be an NP, we know that with the help of a fairy godmother, we could check the solution is valid, right? If the solution it was given to us, we can check it in poly time. We also want to prove that it's hard. It's NP hard, meaning it's hard is everybody in NP. Right? So what does that mean? That if you could solve it fast, you could solve every problem in the class fast. It says for every problem in NP, you have to prove that our new problem is at least as hard as it. If you could solve this problem, you could solve everybody in the class. Right? Is that making sense? No, the halting problem is NP hard. Because if you could solve the halting problem, you could definitely solve everybody in NP. Right? But the halting problem is not NP complete because it's not in NP. Right? So Cook proved that SAT was an NP. So all we have to do is to prove that a new problem is at least as hard as SAT. So for example, 3 coloring is at least as hard as SAT, and SAT's at least as hard as all of these other problems. So we know that 3 coloring is NP complete. Right, so a new problem is NP complete if it's NP and it's NP hard. Right? That's our NP complete class. And as I said, Cook proved that SAT was NP complete, not SAT is co-NP complete. And this is kind of what I was saying before. You take any reasonable problem that's an NP, then it doesn't take too long before somebody either proves that it's polytime or proves that it's NP complete. The only exceptions are given a big integer, can you factor it? And given two graphs, are they the same? Are they isomorphic? Are they the same except for reordering the nodes? So those problems are believed not to be NP complete and not to be polynomial. And those are the only 2 problems I know about. All right, then how do we do a reduction? Right, there's the code for the reduction. Remember? And that's all we're going to do. Any questions about this? Traveling salesman is NP complete. Yeah. Any questions about it?
Professor, so you just have a random problem in front of you. Like, how do you quickly determine if it's NP complete? Just quickly. Any shortcuts to do that?
knowing whether it's an NP should be fairly easy, right? Given an instance that's a yes instance, is there some witness that if the fairy godmother gave it to me, I could prove to my boss that it's a yes instance in poly time? All right? And if I were to give you a new problem, you should be able to recognize that it's an NP. Knowing whether it's NP complete takes a lot more finesse and training than I would expect you to be able to do. Yes?
For NP completion, we prove that it's harder than NP complete, and the NP complete problem should be harder than the problem because we got equally, right?
Yeah. So in general, right, if it's, you want to look at how many solutions there are, right? And if there are an exponential number of solutions, and they seem to be all subsets, then they could well be NP complete. But, I mean, the reason we look at network flows is because there are an exponential number of different flows, and yet it happens to be poly time. There's some problems that kind of surprise people. Any other questions? NP going once, going twice?